reactions and all of that fun stuff, and then we're going to relate it back to thermodynamics, right? So we're going to come up with a relationship between standard electrochemical potentials and work, and how does that relate to the Gibbs free energy equilibrium constant for these systems. So we'll probably get through the ideas of balancing, redox reactions, half reactions, and stuff today, and talk about the thermodynamics on Thursday. Okay, so for redox reactions, we know that they compose of two components, right? So you guys should have heard of this at some point in your chemistry career. A redox reaction composes of what two processes? What two processes comprise a redox reaction? Oxidation and reduction, right? So I have them right here for you. So I was hoping I get a little bit more participation on that one. Oxidation is what? What is the process of oxidation? Losing electrons, right? We lose electrons. And reduction is gaining electrons. And so how are we going to relate this to thermodynamics? Well, if you have two standard cathodes and electrodes, right, they might have a difference in potential between them, right? Which means that at one electrode, you may have a redox reaction happening, and at the other electrode, you may have the opposite, a reduction reaction, and the other one would be an oxidation reaction. And that's going to allow for movement of electrons through these systems, right? So based off of the potential in this cell, you can determine if a process is going to be spontaneous or not. So in any ionic bond formation, there's usually a redox reaction because one atom is going to accept electrons and the other one is going to lose electrons. So if you have an element in its natural state, what is the charge on that element? Yeah, so for magnesium, what is the natural oxidation state of the magnesium? It's positive 2. And before it comes in contact with an anion, right, that it can transfer its electrons to, it's 0, right? So you'll have something where you have, it starts off with a 0 charge, and then when it forms an ionic bond, it goes to a +2 charge, right? And the same thing with sulfur. Initially, it's at a, try and make this pretty, a 0 charge, and it ends up as 2- to form a neutral ionic compound, right? So which compound gets oxidized and which element gets oxidized and what gets reduced? Sulfur is reduced because it gained electrons, it gained a negative charge, and the magnesium is oxidized, right? So magnesium in this case and sulfur in this case is what gets reduced. And so this whole reaction, this net equation, is a redox reaction because one thing's getting oxidized and the other one's getting reduced. That's how we define a redox reaction. You can define these redox reactions in terms of what's called their half reactions. And what half reactions look at is just the movement of electrons in the oxidation process and the movement of electrons in the reduction process, right? So one of the reactions is represents oxidation, and the other one represents reduction. So if we look at the process here, each of these are called a half reaction. We see that the magnesium, it loses 2 electrons, so that means one of its products are 2 electrons, right? Losing 2 electrons, the same way when we think about exothermic reactions, we think of the heat as a product, right? Because you lose heat to the surroundings. In a oxidation process, you think of the oxidation as losing electrons, so those are products in the half reaction. The reduction reaction, we gain electrons, so electrons are treated as reactants in that reaction. Right, so here electrons are reactants in the reduction reaction. And then the net reaction, which gives us our redox reaction, is the sum of these two. So this is the redox reaction for the entire system. But we can analyze it in terms of the half reactions, one being the oxidation and the other one being the reduction. And so to get the net equation, which is the redox process, you need to balance these half reactions sometimes. And what that means is that you want equal charge on both sides of the reactions, right? We have charge neutrality, so we should have equal charge on both sides of the reactions. And you need to have the electrons not as products or reactants, right? So electrons should cancel out. So in balancing half reactions, the original tabulated reaction would probably look something like Ag plus an electron goes to AgS, something like that. That would be our original half reaction, because the oxidation state of silver is +1, right? Silver is one of the few transition metals that has a fixed oxidation state, so it's a type 1 cation. It has a +1 oxidation state. And so to balance a half reaction, to get a net reaction, you just need to make sure that everything cancels out. So if you multiply the original reaction times 2 here, it allows the electrons to cancel out on both the product and the reactant side of the reaction, right? We have 2 here now, 2 on the product side, and so these then cancel out to give us our overall, and again, this was called our redox reaction. Right, and so it might be a good time to then take a second to review what are the preferential oxidation states for different elements, right? Because when we're looking at redox processes, the first thing we're going to have to be able to do is identify the movement of electrons, which means we need to be able to identify what's being oxidized and what's being reduced. In a reaction like the copper-silver reaction here, or in the magnesium sulfide reaction, those are relatively simple to look at. But what if we have polyatomic ions, we have covalent compounds in there, right? Because we can have oxidation of organic compounds as well. We can have reduction of organic compounds. That's going to make it a little bit more challenging, right? So we need to be able to identify movement of electrons. So we're going to dedicate a lot today to doing that. And so for the different oxidation states based off of group number, let's take a second to review that. Oxidation states of elements, right? They're based off of the group number that the element is in, right? So if we have 1, 2, 3, 4, 5, 6, and 7, right? The oxidation state is another way of saying what for the element? Does anyone remember? Can we describe the oxidation state? So I know you guys said the magnesium is 2, right? What is 2 for that magnesium oxidation state? What does that number 2 represent? What kind of bond did it form with the sulfur atom? It was an ionic bond, right? So the 2 was the charge of the magnesium ion there. So the oxidation state is another way of phrasing the charge of the atom, or the partial charge of the atom, so on and so forth. It can get more complicated. But the oxidation state is the charge. So group 1 elements have a preferred charge of what? +1. Group 2 is +2. Group 3, really, I put +3, but I'm going to put a star next to that because that's a variable, right? Boron, aluminum, those ones can be a little more complicated. And as we go farther down the periodic table, right, the atoms get even weirder, right? They add more complicated electron orbitals, so they start to behave weird. Group 4 is going to be 0, right? Carbon likes to, be neutral. It doesn't like to form any type of ions generally. 5 is where we start to switch sign, right? We go from being positively charged to now forming anions. So something like nitrogen prefers to be -3. That's not always the case, but it prefers to be something -3 in an ionic compound. And then group 6 would be like oxygen and sulfur. Those like to be what? -2. And then the halogens are -1, right? And so these are the preferred oxidation states for elements, right? So this gives kind of a good starting point. And the -2 and -1, these are going to be important most of the time. Important. And then the +1, these are also generally important. The larger values for the charge, like +3 and -3, those can be variable sometimes in, for example, polyatomic ions. And I'll talk about what that means in a second. And so we have our standard groups, and then we have the transition metals, right? And those transition metals are generally special because, for minus a few exceptions like silver, they're going to have variable oxidation states, right? They can form multiple different charges on the element themselves. All right, so this is based off of their group number, which is the columns on the periodic table. All right, any questions so far? No? All right. So in the next example, we're going to look at a reaction of tin with nitric acid, and we're going to see how do the electrons move between our two reactants, right? And we're going to see how can we determine the movement of electrons in a redox reaction that isn't so straightforward like magnesium sulfide was. So if this is a redox reaction, which it is, determine which element is oxidized and which is going to be reduced, right? If we have elemental tin, what should the oxidation state of that be, right? Tin is SN. 0, right? We haven't transferred any electrons yet, so that should be 0. So now we need to look at our polyatomic ion, right, which is nitric acid in this case, which forms nitrate. And this one's going to be a little bit harder to determine. So I mentioned the +3 and the -3 elements. Those ones are a little less important for determining the oxidation state, whereas +1 and -2, -1 and +2, those are going to be a little bit more important. And so what we're going to do is hydrogen is always going to be +1, and oxygen is always going to be -2. And we're going to look at, based off of those two values, which we know to be true, to see what the oxidation state is on the nitrogen, which is going to be the central atom in this molecule. And we know the overall charge on that molecule is what? Of this nitric acid. What's the overall charge on this molecule right now? 0, right? So this is going to be overall neutral. And we're going to use that in combination with our definitions of what hydrogen and oxygen are to determine what the oxidation state of nitrogen is going to be. Right? So if we have one hydrogen, what's the charge associated with that? +1. And if we have 3 oxygens, what's the charge going to be associated with 3 oxygens in that molecule? -6, right? So this is going to be -6. So for overall, for the molecule to be neutral, what does the charge on hydrogen have to be? +5, right? Because we have +1, -6, which gives us -5 right now. To make that neutral, we need a +5 to counteract that, right? So +1 -6 equals -5, which means nitrogen has to be +5 to equal 0 for this molecule. All right, so we've determined the oxidation state of the nitrogen in our nitric acid compound. And now we'll look at what happens in the product side, right? How has the movement of electrons affected this redox process? So for tin, what is the new charge on our tin molecule? What is the charge allocated from 2 oxygen molecules? -4. And what about the tin? What's the tin going to be? What is the charge on that ionic compound? It'll be +4 because overall tin oxide or tin 4 oxide is going to be neutral, right? Because we have ionic compound, the positive and negative charge cancel each other out. So that's going to be +4. Okay, what about the nitrogen molecule? What is 2 oxygens for the nitrogen dioxide, NO2? What's the charge from 2 oxygens? -4. And then the nitrogen is going to be what to make this neutral? +4, right? And so now we can look at the nitrogens. We could look at the water molecule too, but that's not going to really tell us much about the movement of electrons because hydrogen and oxygen aren't going to be oxidized or reduced in these cases. Why? Because we actually analyze oxidation and reduction in terms of movement of oxygen and hydrogen, right? It would be like saying, if those were two electrons right there, did the electrons get oxidized or reduced? It doesn't necessarily make sense, right? So we're not going to look at H2O for that reason. We're looking at the other heteroatoms that are not hydrogen or oxygen. And we'll see when we're in different solution conditions, whether it's acidic or basic, how we can balance these half reactions using the fact that the solution is acidic or basic, right? So let's look at the two different processes that could happen here. What happened to tin? Was it oxidized or reduced? It was oxidized, right? Because we went from a charge of 0 to a charge of +4, which means we lost 4 electrons, right? So tin gets oxidized, right? So the half reaction would be tin goes to SN4 plus 4 E minus, right? 4 electrons we lost on tin. And what about nitrogen? What happened to nitrogen? Right, nitrogen went from what charge to what charge? Went from 5 to 4, so that means it got reduced. It gained 1 electron, right? It went from a large positive charge to a slightly less positive charge. So nitrogen gets reduced. It went from nitrogen 5 plus to nitrogen 4 plus an electron. Now we wouldn't write the half reaction like that because that's not actually the molecule that is getting reduced, right? But we see it in the nitrogen in that molecule, right? The actual half reaction would be that we would get HNO3 goes to NO2 plus an electron. And to get the two, it's going to be on the reactant side. Plus an electron goes to that, and then plus an electron goes to NO2. And we see that we have 4 total electrons transferred because this reduction process happens 4 times for each nitric acid molecule, right? So the stoichiometric coefficient is important here because that happens 4 times for this reaction. Every time the reaction happens, we transfer 4 electrons to 4 different nitric acid molecules. Okay, so that's how we determine the oxidation states for more complicated molecules like polyatomic ions in redox processes, right? Because it's not just in simple ionic bonding that redox processes happen. It can be in terms of ionic bonds forming, and a lot of times when we're looking at voltaic cells and electrochemical cells, you are looking at simple reactions happening at each electrode. But we have to be able to do it for multiple systems. So let's see if you can figure out what happens in our zinc sulfide here and write down the half reaction for the oxidation process and for the reduction process and how that adds up to the net reaction. So what's getting oxidized and what's getting reduced here? What's the half reaction for oxidation? The zinc is going to be oxidized, right? Because the zinc is going to be losing electrons. Metals generally lose electrons in these processes. So zinc goes from zinc solid to zinc, and what's the charge on zinc going to be? 2 plus. I guess I'm not going to put the state of matter. Plus 2 electrons, right? That's our oxidation process because we lost 2 electrons. If we have the reduction reaction, that means that sulfur is going to be reduced. And what is the reduction reaction here? S plus 2 electrons is then going to give us S2 minus. Right, that's our reduction process. And when we add these up, we get the net chemical reaction, right? The electrons should cancel out on both sides, and the charge should be conserved on both sides of the reaction. Okay, so that's a simple redox process, right? It's a little more complicated when we have polyatomic ions and covalent molecules that are involved. But for those ones, again, we're looking at the change in oxidation number for the central atom in those molecules. Okay, and so when we're balancing these reactions, it isn't always a straightforward process. It depends on the type of solution that we're going to be in. So whether or not we're in a acidic or basic solution, we're still generally looking for net charge on the product and the reactant side being equal to 0 and conservation of mass. So with redox reactions, the only thing that's different for balancing a redox reaction compared to a normal chemical equation or chemical reaction is we're not just looking at conservation of mass, we're now also paying attention to the conservation of charge, right? The charge on the reactant and the product side, the overall charge when you add everything together should be the same, right? So now we're looking at conservation of charge as well. And we can neutralize charge in our redox processes because we have source of ions in basic or acidic solutions. So what ion do we have present in acidic solutions? How do we define the acidity of a solution, if it's acidic or not? The concentration of what? Yeah, hydronium ion, right? So we have a source of H plus ions in acidic solutions, right? And in basic solutions, we have a source of what? OH minus, right? We have OH minus in basic solutions. And so to balance the charge in redox processes, we can add hydroxide or hydronium to reactants or product sides. And then because now we've added another element, we can balance the hydrogen or oxygen, now that we've added oxygen and hydrogen, with neutral water, right? Because in our acidic and basic solutions, we also have water. We're dealing with aqueous solutions. And so the general procedure is going to be to assign the oxidation numbers, write out each half reaction, then you balance the half reaction according to the number of atoms, right? So make sure you have the right heteroatoms on each side, and then you look at the charge. And the charge, you want to make sure the electrons are balanced on the product and reactant side so they cancel out, and then you can add the two resulting reactions to get the net reaction. Right, so there's two different processes for this, one for acidic reactions and one for basic reactions. And really all that's different between them is your source of charge, which is either going to be hydroxide or hydronium. Okay. Anyone still writing this? Am I going to move on? And so for an acidic solution, right, you balance based off the charges in an oxidation number, right? So looking at the individual half reactions after you write them out. You balance the other elements besides O and H, right? So this is like nitrogen, zinc, whatever other heteroatoms you have present in the system. And then you're going to balance oxygen and hydrogen. And so when you've adjusted the number of other heteroatoms, you probably changed the number of oxygen and hydrogen. And so to add hydrogen or oxygen to one side to balance oxygen, you just add the equivalent number of water molecules to the oxygen deficient side. And what that means is you add H2O to the side that needs oxygen. Right, so whatever side needs oxygen, meaning that there's more oxygen on one side of the half reaction than the other, you add water to the other side. Right, so remember when we looked at that example with nitric acid, we had water molecules on one side. Those water molecules are there because we go from nitric acid, which has 3 oxygen molecules per nitric acid, to nitrogen dioxide, which has 2 oxygen molecules per nitrogen dioxide molecule. I'll just quickly jump back real quick just to show you what I mean, right? So here, not this one. For this one right here, right, we needed water there because we have less oxygens on this side of the redox process, right? So this is in this half reaction. This would be how we balance the reduction half reaction because oxygen is not balanced here, right? Oxygen, we need one more oxygen here. So we would add a water molecule to that. And so after, let me go back here. After you've balanced the oxygens, then you're going to balance hydrogen just by adding H plus to the deficient side. All right, so you can add just straight hydrogen ions. If you added hydronium, that's fine. You would just have to account for adding more water molecules to the other side, right? If you add a water molecule to one side and hydronium molecule to the other side, that's a net addition of one hydrogen to one side. Right? And so after you've balanced the hydrogens, then everything should be fine and dandy. The charge should be neutral, and all the elements should be balanced in your reaction. And then you add them together to get your final equation, right? And so you should have charge neutrality. So this is the conservation of charge, and you should have the conservation of mass. All right, and the conservation of mass is just, do we have the same number of each atom on both sides of this redox reaction? Okay, and we'll go through examples of this. I'm just going through the stepwise process for both of these. And so for balancing the half reactions in basic solutions, now our source of charge is going to be hydroxide ions, right? So we have hydroxide ions in our solution. Oops, how did I go all the way back there? Right, and so we do the same, the first two steps are the same, right? We balance the number of electrons on either side of the half reaction, meaning the electrons in our reduction reaction on the reactant side, and the electrons on the product side of our oxidation reaction should be the same. But then we're going to balance oxygen and hydrogen differently. So to balance oxygen, we add 2 hydroxides to the deficient side and 1 water molecule to the other side. And so what that looks like is if we have 2 hydroxides to one side of the reaction and we add 1 water molecule to the other side, we see we've added 2 hydrogens on the left, and on the right, how many hydrogens have we added? 2 as well, right? And on the left-hand side, we've added how many oxygens? 2. And how many oxygens have we added on the right? 1, right? So that's a net addition of 1 oxygen on the left-hand side here, right? And that doesn't mean it's always going to be the left or the right-hand side. It's whatever side is oxygen deficient, whichever side needs more oxygen, right? So this would be the deficient side. In oxygen on the left-hand side of this reaction. And so then I guess it's already there. After you've balanced the oxygen, so that means if you needed to add 2 hydrogens to one side, what would the total addition look like on both sides of the reaction? Yeah, on one side. Let's say your deficient side, right? You needed to add 2 oxygens to that side to balance the oxygens on the right-hand side of the equation. So if I have, right, man, where did it go? So if I have, this is my deficient side, this is my reaction arrow, and I need to add 2 oxygens to the deficient side. How many hydroxide ions would I add to that side? Right, when I did it for 1 oxygen, it was 2H minus on this side, and I added 1 molecule of water on the other side. Right, which means I've had a net plus 1 oxygen atom on this side. What if I want to find a net plus 2 oxygen atoms on the product side, the deficient side, or the reactant side, sorry, the deficient side. How would I do that? How would I add two oxygen molecules, or sorry, no, two oxygen atoms on the reactant side? We're gonna, for the product side, we're definitely gonna add two water molecules, right? And how is that gonna be to net two oxygen atoms on the reactant side? What do I need to add on the reactant side? Four, right? We need to add 4 hydroxide ions, because now we have 4 oxygens here and 2 oxygens there, which is a net 2 oxygens on this side. Right, so when we need the number of oxygens we need, is equal to, or to balance that, we multiply the number of oxygens times 2 equals the number of OH ions on the deficient side. So the total number of oxygens that we need to balance the half reaction, we take the number of oxygens we need times 2, and that's how many OH ions we have on the deficient side. For the side that we aren't adjusting the number of oxygens, we need to, at the same time, add the number of H2O molecules equals the number of oxygens needed to balance the half reaction. Right, so in the first reaction, we only needed 1 oxygen to balance the reaction. So we only added 1 water molecule. In the second one, we needed 2 oxygens to balance the reaction, so we added 2 water molecules. Right? Whatever we do to the other side, the side that needs oxygen, we have to multiply by 2 the number of added hydroxide ions. Right, so when we're in, and this is only in basic solutions, right? Because that's why we're dealing with hydroxide ions here. To balance oxygens for our polyatomic ions, most of the time is where we're going to be doing this. And then to balance the hydrogens, we add 1 water molecule. Right, so this was for oxygen. To balance the hydrogens, if this is the deficient side, we add 1 water molecule to the deficient side, and then a hydroxide ion to the side that we're not adding any hydrogens to, right? The deficient side, what that means is just the side that needs hydrogens. Because now we have how many hydrogens on the left side? 2, and how many hydrogens on the right side? 1, right? Which means that we've added a net 1 hydrogen to the reactant side here. And the idea here is that you're going between H2O and OH minus. In the redox process, right, you're getting association and dissociation of hydrogen, which is associated with the oxidation reduction process. We can think of oxidation and reduction in terms of movement of electrons, or movement of hydrogens, or movement of oxygen molecules. These are all ways that we can define reduction and oxidation. Right, so we're looking at that as the movement of these molecules and how that balances on either side of the reaction as well. Right, and so whenever we go from H2O to OH minus, that means we're adding 1 hydrogen to a molecule on the reactant side. And then afterwards, you just check to make sure that your charges are balanced on both sides and all the conservation of mass and charge is there, right? So we're going to check again for conservation of charge and conservation of mass, right? Do we have the same number of elements, and is the charge the same on both sides of the reaction? So these are the 2 processes. These are the 2 different solutions that we can balance our redox reactions in. And again, this has to do with the fact that redox reactions can also be defined in terms of the movement of oxygen and the movement of hydrogen as well. Adding hydrogen is the same thing as adding electrons. Adding oxygen is the same thing as removing electrons. Okay, any questions on that? Okay, so here we're going to have a redox process, right? Balance the following redox reaction in acidic solution, right? That means we're going to use the first method to balance this reaction. So the first thing that you do is you write the oxidation numbers for all of the elements that are being oxidized and reduced in this reaction. Zinc is 0 because why is zinc 0 and not charged on the reactant side? Yeah, it's in the solid state. It's a lone metal atom, right? So that's going to be neutral charge. Oxygen is nitrogen is +5 in this nitrate ion. Why is it +5? What's the charge from 6 oxygens? Or sorry, 3 oxygens. It's -6, right? It's -6 is the charge from 3 oxygens. And the overall charge on that molecule is what? -1. So when you add these together, that gives us -1, which is the overall charge on the molecule. So that's why nitrogen here is +5. Zinc on the other side, it gets, what happens to zinc? Does it get oxidized or reduced? It gets oxidized. It goes from zinc 0 to zinc 2+, right? So it loses 2 electrons. And then now we have hydrogen, right? Which is another way we can look at oxidation and reduction. So hydrogen adds what charge to the molecule? +1, right? So 4 hydrogen should be what? +4. Right? Each hydrogen has a +1 charge. And the overall charge on this molecule is what? For ammonium. +1. So when you add these together, you get a +1, which is the overall charge on the molecule. Right? So the way you determine the new oxidation state of nitrogen is because you know the overall charge is +1 and each hydrogen is +4, which means that nitrogen has to be -3 in this case. So nitrogen goes from +5 to -3. So it got reduced and it gained 8 electrons in this process. Right? And you say, well, that seems like a big change. It is a big change because nitrate has 3 oxygens to it, and it's getting reduced by 4 hydrogens now, each nitrogen atom, right? Adding nitrogen is like the same thing as being reduced, right? So that's how we can also rationalize that nitrogen is being reduced here. And so the half reactions are zinc loses an electron because it gets oxidized, and nitrogen gains 8 electrons because it gets reduced. So that's, we go from a charge of +5 to -3. We gained 8 electrons. And so before we balance the elements on each side of the half reaction, how would we balance the charge here? What would we do to balance the charge in these two half reactions, right? We want the number of electrons to be equal on the product side of our oxidation and on the reactant side of our reduction. So what would we do to the first reaction? Yeah, we have to quadruple it, which is like multiplying this whole reaction times 4, right? And now we at least know the electrons are going to be balanced on this. And to be honest, when you look at that, okay, that's probably going to balance the charge for this reaction, so this will probably be okay for our final because there's no movement of oxygen or hydrogen in this half reaction, right? We don't have to balance oxygen or hydrogen the oxidation reaction doesn't need to balance at all. However, for the reduction reaction, right, we do have hydrogen and oxygen on both sides of the reaction that need to be balanced, right? Here we have oxygen and hydrogen on both sides. These need to be balanced. And so this is where we use the method that we talked before. To the oxygen deficient side, we're going to add water molecules. Into the hydrogen deficient side, we're going to add hydronium or hydrogen ions, right? H+. And then we should see that the the overall charge should be the same on both sides of the equation when we do that. Because now we have a -9 on the reactant side of our reduction reaction and a +1 on the product side, right? So charge is not conserved here. So there's a couple things to realize. We need charge isn't conserved, right? This is -9 over here, and this is +1, right? So the charge isn't conserved for our reduction reaction. What about our oxidation reaction? Is charge conserved? Each electron carries what charge? -1, and we have how many electrons in that process? 2, so we have -2, and what's the charge of the zinc ion on the product side? +2, right? So the total charge on the product side is 0. And what's the total charge on the reactant side of our oxidation reaction? 0. So the charge is conserved for our oxidation reaction. We don't have to worry about that. When we do the balancing of the oxygens and the hydrogens on this side, that will solve our problem of charge neutralization, right? We can't just throw in electrons wherever we want, but we can supplement charge with our hydroxide and hydronium ions in acidic solutions, hydroxide in basic solutions. Okay, so let's see how we go about this, right? So we're probably going to need to first identify what the oxygen deficient side is. So what's the oxygen deficient side here? It should be the product side, right? Because we don't have oxygens, and we have oxygens on our reactant side. So this will be the oxygen deficient side. And the hydrogen deficient side is then going to be what? The reactants, right? This is our hydrogen deficient side. And we could do, you don't have to write this out and do this step, but it's good to identify this because now we know what sides we're going to be adding what to, right? Oxygen deficient side, we add our water molecules. In hydrogen deficient side, we add our hydrogen ions, right? Our hydronium ions. And so just based off of observation, we're missing how many oxygens from the right-hand side for a reduction reaction? 3. So how many water molecules should we add? 3 water molecules, right? So we'll do that first, and then we have to reassess the number of hydrogens to see how many hydrogen ions we need to add to the other side. That's why we do the water first, or the oxygen first, because we can always add hydrogen very simply. Hydrogen is very easy to add. Okay, am I good to go on? All right, so the first thing we do is we add the 3 water molecules, right? And now we've balanced oxygen when we add the 3 water molecules. And so we need to then add H+ ions to balance the hydrogens that we've just added to both sides, right? So how many hydrogens are from the water molecules we added? So this is 6 H that are added, and how many are in the ammonium ion? 4. So we needed to add how many to the other side to balance the hydrogens? 10, right? So we add 10 hydrogen ions. And now if we look at the total charge on both sides, right? So we balanced not the heteroatoms, nitrogen, which was already balanced. We don't have to do anything with that. We balanced the oxygen first by adding water molecules to the deficient side. Then we balanced hydrogen by adding H+ to the hydrogen deficient side. And if we look at the charge now, we see that we have 10 positive charges and 9 negative charges. So we have a +1 on the reactant side and a +1 on the product side now, because ammonium is our only source of positive charge on that side. Right, so now both sides of the chemical reaction, we have the charge balanced. And so once you've done this, then you just add the 2 half reactions together, and that gives you your overall reaction. That gives you your net redox reaction. And the reason this is important is because it tells us a lot about the movement of electrons. Right? It tells us how many electrons are being transferred in this reaction. And so you add them together, we see that the electrons on both sides cancel out, which is what we want, and we get our overall net reaction. We see that the mass is conserved because we have the same atoms on both sides of this reaction, and the charge is conserved because we have the same net charge on both sides of this reaction. All right, so this would give us our final redox reaction. This is our total redox reaction. How all the water molecules and hydronium ions are present and involved in the redox processes, right? Because that gives us a source of hydrogen and oxygen. That gives us another way to think of oxidation and reduction processes. Okay, any questions on that? So on the practice exam, there will probably be an example of you balancing something in an acidic or a basic solution. In the basic solutions, it is a similar process, except what we're adding is slightly different. The basic solutions are a little more annoying to deal with because to add oxygen, we need to add water to one side and hydroxide to the other side. So we can do a quick review, right? So in basic solutions, the half reactions, to add one oxygen to the deficient side, we add two hydroxides to that side, and one water molecule to the other side, right? That's a net zero change in hydrogen, but a net change of one oxygen atom. To balance hydrogen, we add one hydroxide to the non-deficient side and a water molecule to the deficient side. That is a net change of 0 in oxygen molecules and a net change of +1 in hydrogen atoms. So if we have another example here, we can balance one of the half reactions just to show how that process works. Here we have manganese 7 oxide. So manganese is just one of the interesting transition elements. It has more oxidation states than any other transition element. We know it's a +7 charge because 4 oxygens is what charge? -8, right? And the overall charge on that ion is what? -1. So it has to be +7 to give a net charge of -1, right? So this has to be, -8 equals -1 when you add those together. Sulfur, if we have 3 oxygens, right? Again, we're looking at oxygen and hydrogen because that's how we determine or can analyze reduction and oxidation processes. The sulfur has to be +4 because 3 oxygens is what charge? -6, and the overall charge on the molecule is -2, so the sulfur has to be +4 there. We do the same thing for the product side, right? -4 for manganese oxide, manganese 4 oxide. The overall charge on that molecule is what? 0, right? So they have to be cancel out. And then for the sulfate ion, we have -8 from the oxygens, and the overall charge is what? -2, which means that we have to have a +6 charge on the sulfur. And so now we can look at the different heteroatoms and see how they get oxidized or reduced, right? Sulfur goes from a charge of what to what? What's sulfur charge on the reactant side? +4, and on the product side? +6, right? So what happened? Did we gain or lose electrons? We lost electrons, right? We became more positive, which means we lost electrons, right? So this was our oxidation reaction. Manganese goes from +7 to +4, so we go to a smaller positive charge, which means we gained negative charges. So that was reduced in that process. So let's balance the oxidation reaction here, right? We don't have any hydrogens yet, but we know we're in a basic solution, right? So we're in a basic solution, which means our hydroxide ions is what we're going to be looking at to use to add water and hydrogen, water and hydroxide ions. So it's SO3 to SO4. So we go SO3, 2 minus, to SO4, 2 minus, I don't know why I drew an arrow there, plus 2 electrons. So what is our oxygen deficient side, the left or the right? The left side, right? This is our oxygen deficient side. And the reason I say it's our oxygen deficient side is because we only have 3 oxygen atoms there and 4 oxygen atoms on the product side. So to add a net 1 oxygen atom, which is all we're missing, to the reactant side, what do we do? Right, we can only use OH minus and H2O, right? But we add 1 to one side of the equation and the other to the other side. So we will need one oxygen on the reactant side of this half reaction. We add water to which side? The product side, right? We add 1 water molecule, right? So we've added 2 hydrogens and 1 water molecule here. And when we do that, what do we have to add to the deficient side to get 1 net oxygen on that side? We add 2 OH minus. Because now we've added 2 oxygens to this side and 1 oxygen to that side. That is a net addition of 1 oxygen on this side. So our new reaction becomes 2 OH minus plus SO3, 2 minus goes to SO4, 2 minus plus 2 electrons plus H2O. Right? When we added the 2 OH minus, the 2 hydroxide, that added 2 hydrogens to this side. Water added how many hydrogens to that side? 2 as well. So the net addition of hydrogen on either side is what? For hydrogen. If we added 2 to that side and 2 to that side, is there a net change in hydrogen? No, because we added the same amount to both sides, right? So same amount, we didn't add any net hydrogen. And so because there's no hydrogens in this half reaction, that means that we don't have to go any farther, right? Hydrogens are balanced, oxygens are balanced now on both sides. And is the charge balanced? What's the total charge on the reactant side? -4. And what's the total charge on the product side? -4, right? So now we have the conservation of mass and the conservation of charge. All right, so we're just going to do this for the one basic reaction. If we needed to add hydrogens, we would just add 1 water molecule to the deficient side and a hydroxide to the other side, right? So all we're doing is we're just adding oxygen and hydrogen in a different way, right? Because we can't just add in a basic solution hydrogen or oxygen, we have to add a combination of hydroxide and water so that the net change is 1 oxygen or 1 hydrogen. All right, so this equation right here is balanced. If we were to go through and balance the entire equation, it will be a little bit more involved just because all we're going to have to do is multiply the top equation by 3, the bottom by 2, so that the net electrons are there. And then we also have to balance the oxygens in the reduction reaction, right? Because which side is going to be oxygen deficient here? The right side, right? We only have 2 oxygens there and 4 oxygens on the left side. Right, so this is oxygen deficient. Because we don't have any hydrogen movement here, we don't, since we don't have any hydrogen movement here, we don't have to worry about balancing hydrogen for this reaction. We also notice that the definitions of reduction and oxidation here hold true for our movement of oxygen and hydrogen that we mentioned, because in the first half reaction, we gained an oxygen atom, right? Which means we were oxidized. In the second reaction, we lost an oxygen atoms, which means we were reduced, right? Again, oxygen follows the opposite trend, hydrogen follows the same trend as electrons, right? So we could think of it in terms of oxygen movement, or in terms of the electron movement, or in terms of the hydrogen movement. But not every system is going to have all three of those. Okay. All right, so there is one other example here. Is it this one? Nope, that's the same example. All right, so let me see if I want to stop here, if I want to keep going. All right, so we'll leave it here for today, and for the lecture at least. And next time we're going to start talking about voltaic cells, which is looking at electrical currents moving through systems where redox reactions are happening, right? So a voltaic cell is going to be one where a spontaneous electrochemical or redox reaction is happening. Does anyone know? Well, I guess the example is right there. Is for batteries, right? This is how batteries work, is they have a spontaneous redox reaction happening. You see movement of electrons. Movement of electrons generates electrical current, and that's what powers your devices, right? Then you have electrolytic cells, where you have a non-spontaneous reaction, but you have the reverse idea. You can run a current through this reaction, and it causes a non-spontaneous reaction to happen. The same way we can raise the temperature for a non-spontaneous reaction to become spontaneous, you can raise or flip the sign of the voltage of a circuit, and that'll cause the reaction to then start happening, become spontaneous, right? So instead of looking at temperature moving across the equilibrium point, you can look at flipping the sign of your voltage. And so we're going to talk about a little bit about the notation of how do we identify or decide where electrochemical cells are occurring, or where the different redox potentials are going to happen. So just a brief intro is you're going to have one electrode is going to be where the redox reduction reaction happens, and the other electrode is going to be where the oxidation reaction happens. And that's because one side needs to be pulling up electrons, and the other side needs to be getting rid of electrons. And that movement of electrons is what generates your electrical current, or the movement of electrons in the opposite direction is what generates the reaction happening. All right, so we're going to look at both of these cases, and then ultimately we're going to relate this back to thermodynamics, because we know how this is related to the equilibrium constant. Well, we can see how does now the voltage across your electrochemical cell affect the spontaneity of the reaction. So the same way we have delta G in terms of enthalpy and entropy, or if we have non-standard conditions in terms of the partial pressures of your gas, or non-equilibrium concentrations of your aqueous reactants, you can now have another step that says, well, what happens if we change the voltage across the cell? How is that going to affect the spontaneity or the movement of these reactions happening? Right, so it's the same type of reactions, it's now specifically we're talking about redox reactions, which is why we just talked about balancing them and understanding a little bit about the movement of electrons. So instead of just energy being released, now we're looking at movement of electrons, because that's related to electrical current. Okay, so we'll stop there for our lecture today, and then we'll